Hello and welcome to class P30 of the resistance welding processes. This particular little presentation has to do with resistance welding challenges. And what I thought I'd do is I'd take a run through the different scenarios that I've come across over the years and see if I can shed a little bit of light on my thought process for solving them. So your thought process has to be based on those four principles of your typical resistance weld. And that is the squeeze, the ramp, the current initiation, of course, and then the cool time afterward. Always keep those principles in mind and you'll be able to troubleshoot it pretty good. But let's take a walk through some of the situations. So here's a typical, we'll call this the perfect joint, the perfect connection, the perfect everything. It's important to note that you're trying to form a nugget based on going through steel. And the conductivity of this steel and the conductivity of this joint are always going to be a little bit in flux. So there has to be some safeties put into your process. Now, when it comes to where the actual materials get hot, you could always take your electrodes and make a situation like this when you make an X on your surface contacts. And wherever the X is in the middle, that's where the heat will be applied. Now, listen carefully, because what I'm going to tell you is that happens even when the materials are unbalanced. It starts in the center and works its way out. So that means that you can take your electrode diameter, your surface contact, and you can start messing around with that a little more to change where you're applying heat inside of your joint. It's not done very often, but sometimes you'll get a very thin. I'm going to give you some examples. I got some great cross sections to show you in a few minutes. And where the outside portion, the outside piece, was very thin, and it was too thin for their cycle to actually get it to weld. And that's where we'll put the icing on the cake for this understanding of this problem. So here's a situation here where we've got a little bit unbalanced thickness. So look at the surface contact that's happening on these. And so we've actually changed it a little bit to try to get the heat to be generated up in the closer to where the two parts meet. And of course, the other way around, this wouldn't work. So where these two blue lines cross is actually where the heat's going to start. We've done lots of examination of these things, and we can see that that's exactly what happens. Now, if you're pushing hard enough, you should be in a very good position to control the heat and to keep this joint nice and tight. Now, this would shift down a little bit if this surface weren't here. If we were making contact in another area, it would come down closer to where we get our joint, because it would increase the resistance. So, but this is not the situation you want, of course. Here's a great example that explains what I'm trying to say. So this is a cross section where they added, and this was not the greatest joint design, but they added a layer of steel on the outside. And their cycle, they were pressing on it, but their cycle, the heat generated in this area, and it was possibly pushing too hard or making too good a contact in this area, and it actually took on no heat. It felt like the material was being pushed up against another piece of material so well that it actually didn't have enough resistance to start generating heat in this area, which we would hope. But you can see where even in this area here, you can see by the structure, everything in this whole area was liquefied, even the center. So it's not like you have two resistance areas here, one here and one here. There's a whole large area that's going to be centralized between these two electrodes you need to concern yourself with. Expulsion is probably one of the worst problems you can have. Every spec has its own material loss limits in it. And that is, if I have two pieces of material and they're two 1 millimeter thick pieces of material and I resistance weld it, the indentation that's made from the caps can be very deep when there's a lot of expulsion, because it's literally a balloon. You're making a balloon, and the balloon's going to burst. And when a balloon bursts with all the pressure of the material that's forming inside the nugget, it shoots sometimes a very, very long way. So you have to consider this as the programmer, a person that's doing it, to make sure that it gets warm and make sure that it actually has a chance to come together before you go ahead and run your schedule to do the welding. This one is clearly a misalignment. And here's a worse misalignment issue. And it's poorly placed. Now, this is going to change things drastically when it fires, because it's actually going to start to distort the part too. Now, this is a little bit exaggerated how far it's off, but you'd be surprised. This one has about half the cap that's overlapped, and I've seen them like that in the field that are simply worn out that way. They didn't want to fix the beryllium copper components they used to make it, so they just let it run the way it was and started to adjust the parameters. Your misalignment could also be like would be holding it apart. There's a lot of issues with the configuration of it being held apart that we have to try to overcome. The last thing I want to do is last thing anybody wants to do is use your resistance welding caps as a method of clamping this job together. Now, in some cases, it's a little bit what we do, but why not get it to a plastic state first? Remember my preheats, the preheat possibility that you could put a small program in to bring it together, but never tie your preheat right to the welding schedule. Get your preheat, bring it together, put a little cool cycle, and then fire. Don't use it to preheat and get everything too hot. You'll end up getting a lot of expulsion for no reason. Misalignments and shunting, this is very common. Shunting is one of the biggest problems we have when we're trying to pull things together on a flange, for example. Sometimes it'll duck down. And when it ducks, it'll come in and it'll actually make contact in a place where I don't want it to be. This is a perfect example of where I would apply a slow and low schedule to bring this together and get it to a plastic state before I actually start doing my welding. I'm never going to let go. I'm never going to release it in this cycle. I'm going to put in this plastic state, let it cool off for about 10 cycles, and then I'm going to hit it with a proper weld cycle. Different configurations, angles, making sure your guns are nice and straight. Expulsion could come from lack of heat, lack of application of force. And if when you get expulsion, if it's coming from the surface underneath the welder, underneath the cap itself, you've got other problems here, right? You're not pushing hard enough. If you're seeing sparking that's coming, like when you first initiate and it's coming from the cap, underneath the cap, that's not expulsion. Expulsion happens at the back end of your cycle. And it doesn't send a spark, it sends liquefied weld metal, parent metal, flying through the air. So know the difference between the two. Because when you start to see a lot of arcing, it's time to start evaluating your current, because maybe you're applying the current before it has the opportunity to get tight enough. There's your first sign right now that something's wrong. If you start to see that, it's time to make a change or establish your timing a little bit. If I were to see arcing on a surface, the very first reaction is to give it more squeeze time to make sure that my forces are all there, to make double sure I have all forces, and then I would see if I still have sparking. If I do, then there's something else I got to change. Something's gone wrong. When we get close to an edge, you got to be a little bit respectful that the edge wants to heat up. The edge of any piece of steel wants to heat up faster than all the rest. So expulsion could come from between your surfaces under these conditions. And literally, it sprays a long way. It actually will go a long way, expulsion, when it takes off. And it's because it's a little heated nugget. You form this nugget, and it starts to develop here in the middle. It starts to develop, and it starts to get hotter, and it starts to get pressure. As it gets hotter, it gets forces. And then it finds a way out, and bang, it goes a long way. Literally squirting out. Obviously, a bad way to go. Okay, folks, if there's anything else I can help with, you can certainly contact me. That was a good overview of some of the challenges. Most of the challenges are pretty obvious when you look at them. Just always make sure your equipment's working okay. Always make sure your alignment's okay. There's a whole bunch of mechanicals involved in resistance welding that you've got to verify every single time. And I mean, if you just can't get to the bottom of your expulsion problem, you probably have a force problem. And that's just as big of a problem as any other you could have. So you can feel free to get in touch with me if you want to dive into this a little bit deeper. Thank you very much for your time. Bye for now.